If you can start recording, please. I used to see two recording. I don't know if this is because two of you start recording or what. Okay. We discussed the low frequency oscillation problem, and to analyze the dynamic stability of the system, we need to linearize the system model. This is the nonlinear model. This is the nonlinear model. We need to develop the linearized model. Linearized model x dot equal to ax plus bu. We need to put the system model as such. X dot equal to ax plus bu. In order to linearize, we need to find the initial condition, and then we can linearize around the operating condition, a specific operating condition. So we have two ways to find the initial conditions of the machine or of the plant. The first one, we started with the some of the constant definition, but let me screen. So this is the generalized model. We have local load, we may or may not. It's quite easy to handle. And this is the transmission line. We may have resistance, we may not. And this is single machine infinite bus. So terminal voltage, current as defined as such. And the V infinite, we can have also the projection of V infinity on D and the QX. So the machine axis D and the QX will be consider our axis here. So delta is the angle defined between EQ prime and V infinity. This is the current, and we derived some of the constants, and that was very important question, equation, sorry. And this is we covered this part, part A, giving the electrical power, real power, reactive power, and terminal voltage. We can find all the initial conditions, VD, ID, VQ, IQ, EQ prime, EFD, and V infinity, and also the angle. So all this can be calculated. The second case is if you are given the real power, terminal voltage, and the infinite bus voltage. Still you can find the initial conditions if we define these angles beta between VT and EQ prime. Again, where is the DX and the QX? This is the QX, come on, EQ prime, this is the QX, and this is the D-axis. So again, we can find V infinity D and the V infinity Q, ID, IQ, VTD, VTQ, and so on. So we can define the angle beta and delta, the angle between EQ prime and V infinity, same definition as before. Gamma, the angle between VT and the V infinity, and the phase angle, which is phi, and so on. So delta alpha, the angle between, or the angle of the transmission line impedance, X over R, and this is constant, and this is should be known. most likely will be 90 if R equal to 0. We have only reactance. This is the definition of beta, gamma, and the phase angle between Vt and I. Of course, from the phasor diagram, that phasor diagram, this is Vt, and this is Eq prime, and this is the current, so this is the phase angle, and this is beta. So if you have this right angle here, so you can, if this is alpha, if this is phi, but this is also phi. So you can write tan beta equal to this over this. And this value, if this is phi, this part is xqi cosine phi, xqi cosine phi. And this part, small part, is xqi sine phi. And this is Vt. So this part is Vt plus this. So this over the summation here gives you the tan beta. So keep this in your mind at the time being. We will, of course, we cannot find beta, and then we still need phi. We still need the current magnitude, and so on. What we know here is the terminal voltage only. So let us continue with the current. Current can be expressed as such from this figure. Current can be expressed as the I1 plus I2. I1 is Vt times the admittance, Vt with angle gamma times the admittance, plus Vt minus V infinity over the impedance R plus Jx. So this is the current here. Gamma is the angle of Vt as defined earlier. And then you have Ve plus Qe equal to this. You can find Ve equal to VBID plus VQIQ as we have before. So if you expand this, V times I conjugate, what is the current angle? What is the terminal voltage angle? Terminal voltage angle is gamma, or current angle is with respect to the Q axis equal to beta plus phi. So you have this here, beta plus phi. This is the current with respect to the quadrature axis. Okay? You can assume, this of course we did it before. You can expand this, and you can replace the current by its component, or in terms of Vt. So you have such equation. So in this case, you can write Ve equal to this. This Ve, which is known, the terminal voltage is known. And this is the parameters of the system. The V infinity is known as a magnitude, the V terminal impedance. So alpha is known also. Alpha is tan inverse x over R. The only unknown here is gamma. So from this equation you can get gamma, the angle of the terminal voltage. This is not needed at the time being. QE is not known, not needed, just for the derivation of the equation. So gamma can be calculated as such. Substituting in I equation gives I with the its angle from this equation. If you substitute gamma here, so then you can have the complex number, so you can get the current and the its angle. Okay, so substitute, you can get where the angle gamma minus phi equal to gamma minus phi, and then phi can be calculated and substitute in beta. You can go back to the beta and substitute, and then having found beta and gamma, the torque, angle, voltage, and the currents can be calculated as follows. Once you have these equations, you can get delta from that diagram, beta plus gamma, VD, VQ, ID, IQ. These are the projections there. And EQ prime. And that's all. We will not focus on the second part, and practically speaking, the second way to find the initial condition needs some measurements from the remote location near V infinity. And on top of that, V infinity also is the infinite bus is not any physical bus, so the measurements will be not accurate. Okay, so if you go back to these equations, to the model itself, to this model. In order to simulate this model, or in order to linearize, we need to know all the initial conditions. So omega equal to 1, this is the initially, plus we don't need to have any, I think if we have delta dot equal to 0, of course at steady state all these derivatives equal to 0. So if delta dot equal to 0, then omega equal to 1. So, and this is usually the case. How much the initial value of Tm? How much the initial value of Tm? It is equal to
Tm.
Equal to what? Initial value of Tm. In order to simulate this system, you need Tm, you need EFD, you need EQ, ID, IQ, all these quantities we found, except the Tm, which is equal to TE at steady state. Okay, so you are given, in the initial condition, you are given the real power, and the VT and Q, VQ and VT. So this is B equal to BM. Yes, this is the initial value of BM here. But what is remaining is V reference. How much is the V reference at the beginning? In order to simulate this nonlinear equation, or to linearize, what is the initial value of V reference? Can we have it? V reference? Yes, of course we can get it. At steady state, this part equal to 0. We already found an EFD from the steady state value of EQ prime equal to 0 at steady state. This is equal to 0. If EQ prime equal to 0, then EFD will be equal to EFD 0 equal to EQ prime 0, which is already calculated before, plus XD minus XD prime ID. So this is all known now. And also at steady state, EFD dot equal to 0, and I know this part equal to EFD. So this part, which is KA times V reference minus VT. طبعا at steady state there is no BSS. There is no signal from BSS. And this signal comes only when we have a disturbance. If we are talking about steady state, UBSS equal to 0. So this is equal to EFD. So KA multiplied by V reference minus VT. The VT is known, given from the initial value. The EFD is calculated here initially. The KA is known, the voltage, automatic voltage regulator gain, which is known. This is parameter should be given. So you can write here V reference equal to EFD over KA plus VT. EFD over KA plus VT. You have a VT initially, which is characterized the initial condition, and the EFD is calculated. KA is known, so you can get how much the V reference at the beginning. So this V reference also should be calculated from the exciter circuit. So by V reference, you can start simulating all these nonlinear equations. Time domain simulation, I mean. Yes, here it is. This is the exciter initial condition. This is the exciter that we will consider in our course. Very simple, as you can see. So we can write EFD dot and the EQ prime dot as we have. This is EQ prime dot, and then we have it equal to 0 at steady state. We can get EFD, and at steady state we can also equate this equal to 0, and we can get V reference equal to VT plus EFD over KA. طيب, now we found all the initial conditions. Let us now develop the linearized model. So let us linearize all these nonlinear equations. We have fourth order model, 3 equations for the machine and 1 for the exciter. So we need to linearize this model, the nonlinear model. We have these 4 equations, and these are the algebraic equations, and these, of course, we found out with the single machine infinite bus. We have this equation in our hand. So this is a very important equation, by the way, especially for time domain simulation, when you need to update the current value at each time step. So in order to find the VD and the VQ, and if you find the VD, VQ, then you can have this. So these are the algebraic equations. So we will consider also the exciter as such. We have only automatic voltage regulator, and if we have stabilizer, this would be the stabilizer structure, which is widely used in real life, lead lag stabilizer. You have gain, and you have this block, and you have this block. This block we will see the function later on, and this is the lead lag. You can have 2 stage, V equal to 2, or 1 stage or 3 stage of this lead lag block here. So you can have an index P here. We will discuss this in details when we go to the power system stabilizer design. This is another structure. You can have this washout block again, and you have two blocks of lead lag compensation. It is not necessarily to have it one block is repeated, and it is not one ST1 1 plus ST2 before we have B. That means this stage is repeated 2 times or 3 times, but you can have also different time constants here. This is also usually the case. This is the linearized model. This is the linearized model that we need to derive. This linearized model is simply, if you go back to these equations and try to linearize it. Can we linearize this one? Assume that we have small change around the operating condition. We have delta omega dot. Instead of omega dot, we have delta omega dot. So we have a disturbance. In mechanical power, we used to have it 0, but assume that we have change in mechanical power. So 1 over m delta Tm minus delta Te minus Td, or d times delta omega, the omega minus 1. Delta dot equal to omega b delta omega. Delta EQ prime dot equal to 1 over TDO prime multiplied by delta EFD and minus delta EQ prime minus XD minus XD prime times delta ID. And you have this one, EFD, delta EFD equal to 1 over TA multiplied by KA times delta V reference minus delta VT plus delta UBSS minus delta EFD. So this is the linearization. But when we say linearization, we need to express the nonlinear equations here to as x dot equal to ax plus bu. And u here is, what is u here? What is the u here for this standard format here for state space representation of linearized model? What is u? Any answer? What?
Mechanical power.
Mechanical power?
Input.
Raise your hand to let me call you. Ramadan?
It's the mechanical torque.
Mechanical torque. Usually mechanical torque would be 0. When we linearize around the operating point, as we mentioned earlier, if you still remember, we assume the delta B mechanical or B mechanical is kept constant, right? Am I right?
Yes.
V reference also we assume it kept constant at the time being. And this It is kept constant unless you disturb the system throughout these parameters. And you need to change the mechanical power. You need to increase it by 10%, or you need to change the terminal voltage by 10%. So you apply here 10% step in V reference or 10% step in mechanical power. So this is should be an externally done. إنما you can say إنه طب let me ask you before asking about you, what are the states? What are X here? What are the states here?
We have 4 states, Doctor.
Let me tell me what are the states.
It's the omega and the delta, GQ and EFT.
Okay. So we need, these are the X dot. We need to express this one in terms of X. And what you have here, you have delta omega dot is expressed in delta TE, and delta TE is not a state. This is okay, delta omega is a state, that's fine. But delta TE is not the state. So we need to express delta TE in terms of the states. Am I right? Yani our task now is to express X dot equal to X plus mu. If these are X, if these are the states, so we need to express all these states, X dot, in terms of X plus BU. Okay, and we will see U here, which is the power system stabilizer input. So this is U. And we are assuming delta Tm equal to 0, delta V reference equal to 0. So we need to express delta TE in terms of the states. We need also to replace delta ID, and the ID is not a state. So this is a state, and this is also another state. And this is a state, that's fine. So you can have here delta omega dot if you want to express it in terms of the states. Delta omega, delta EQ prime, and delta EFD. So you will say here this is equal to omega B multiplied by delta omega 0, 0, 0. So this is delta dot as A. This is the row corresponding to delta dot multiplied by the states here. But here you need to, this is okay, ready, but this is not ready. You need to express delta TE as states, in terms of the states. Okay. What else? The ID also. You need to express the ID in terms of the states. Here we have delta VT also. Delta VT is not ready. We need to express delta VT in terms of the states in order to write the linearized model, which is X dot equal to AX plus BU. Of course, if U is considered as UBSS, you can write the P matrix here. What do you think the P matrix? If we say, and this is UBSS, what would be the P matrix? Can anybody tell us what is B matrix here? Yeah, Abdul Rahman, Ramadan.
Yes, Doctor. So it's 0, 0, 0, 0.
0, 0,
0, 1.
0, 0, 1.
Yes.
Lay 1. Why 1? What is the coefficient of UBSS?
Okay. K over TA.
Ka over TA. Ka over TA. So this is the B matrix here. This is the input. So our task now is to find an expression of delta TE in terms of the states, ID in terms of the states, delta VT in terms of the states, in order to write x dot equal to x plus BU. So this is our task now. So this is called the Phillips-Heffron model. This is the Phillips-Heffron model, and this is very famous, known linearized model of the synchronous machine, Phillips-Heffron model, or K1 to K6 model. Then we have here 6 linearization constants, K1 up to K6. We will derive K1 up to K6, which is shown here in this linearization model. So this is the linearization model. You have here 6 constants, K1, K2, K3, here, K4, K5, and K6. And if you look deeply here, you can see that this is delta B mechanical, and this is delta B electrical. And this delta B electrical is a summation of 2 components. K1 comes from delta delta, and the K2 comes from delta EQ prime. And that means we can express, and we will derive this, by the way. We can express here delta BE, or delta BE, electrical power, equal to K1 times delta delta plus K2 times delta EQ prime. If this is the case, we express delta power, electrical power, in terms of the states, delta delta and delta EQ prime. Right? The same for VT. VT here, you have here delta V reference minus delta VT, and delta VT is summation here, delta VT equal to K5 multiplied by delta delta, delta VT equal to K5 delta delta plus K6 comes from here, from this signal, which is delta EQ prime. So this is plus K6 delta EQ prime. That means you express also delta VT in terms of the states, delta delta and delta EQ prime. And also this K3 and the K4, we will derive also them during this question. Of course, if you consider delta BM equal to 0, so this delta B will come directly here, and forget about this now at the time being. This is the UBSS. It is not from the Phillips-Heffron model. You can put here any stabilizer, BID, intelligent controller. You can have lead lag or any nonlinear controller, but this is not. So the signal here is UBSS. This signal is the stabilizing signal. So if there is no change in delta V reference and there is no stabilizer, so delta VT will go to the regulator here, which is Ka over 1 plus SCTA. To clear this block diagram little bit, Let us consider this block diagram. Delta Tm here, which is 0, خلاص we neglect it. Delta Vm, and we have here delta V reference, which is also 0. So these the two components of Vt, and these are the two components of Be, which is K1 delta delta and the K2 delta Eq prime. The terminal voltage K5 delta delta plus K6 delta Eq prime. So this is the terminal voltage. K4 and the K3 we will derive it soon. طيب, how to reach to that conclusion? Now we here mentioned that in the delta B equal to K1 delta delta plus K2 delta Eq prime. How to reach to this conclusion? How can we derive this? And what is the value of K1? What is the value of K2? If you go back to the equation, power equation, B, B equal to what? B equal to Vd Id plus Vq Iq. Can you linearize this? Can you get a delta Be? Can you linearize? What do you think? If you linearize this one around an operating point. So this is equal what? Can anybody tell us if we need to linearize this equation? So what do you think the output here? Any answer? Of course, you can replace Vd by Vd plus delta Vd. Id is Id plus delta Id, and then you can proceed. So you can write here B plus delta B equal to Vd plus delta Vd times Id plus delta Id plus Vq delta Vq. Assume that when we have some perturbation around the initial condition, and the Vq Iq plus delta Iq. Of course, you can expand. This becomes Vd Id and the Vq Iq, and this Vd Id Vq Iq will go with this value B. So the remaining will be equal to delta B. So you can write delta B equal to Vd delta Id plus Id delta Vd delta Vd times delta Id, assuming that this deviation is very small, we will neglect delta square. Delta Id, delta Iq, we will neglect it. Plus, Vq Iq will go with this power here. So you have here Iq delta Vq plus Vq delta Iq. And again, the second order of this delta square will be neglected. So this is the delta B. طيب, can we express delta ID and delta IQ, delta VD and delta DQ in terms of the states having these algebraic equations? So in matrix form, you can express VD equal to XQ IQ This is VD, algebraic equation from that model. And VQ equal to EQ prime minus XD prime ID. And this is also another algebraic equation in this model. It is not a problem. We have here these two equations. We'll put them in matrix form. So VQ equal to, you have here ID and IQ and EQ prime. And ID and IQ also, you can express them in terms of VD and VQ, or VD and VQ, you can replace VD and VQ also here. So you can have ID and IQ in terms of EQ prime and delta. So this is exactly the case that we need to reach. We need to express delta ID and the delta IQ in terms of delta EQ prime and the delta delta. Of course, if you have delta ID and delta IQ, you can have delta VD and delta VQ from this equation. So this is what we need to find out here. So this is VD and VQ expressed in matrix form. Just for simplicity and derivation, recall the equation. This is the very important equation. The ID and IQ. If you express the VD and the VQ here, you can get the ID and IQ in terms of EQ prime and the delta. So substitute the VD and the VQ. You can have ID, IQ equal to these constants multiplied by EQ prime, and you have this V infinity sine cosine will be multiplied. Of course, طبعا you need to multiply here by the inverse of this matrix. So this matrix multiplied by inverse. So if you multiply by inverse with C1 and C2, these are constants, and you express VD and VQ in terms of this. طبعا of course the ideal IQ, you can bring them, you can combine them with this term. So you can have this equation at the end. Are you following, يا شباب? Is there any unclear? Is there any clear? Is there any clear thing? You have it here, Ayub Horani.
Doctor, are we supposed to memorize these equations all?
Not all, but at least you can proceed. And we will not ask you to memorize such equation, but this equation, can you derive it?
Yes.
That's fine. That's what we need.
So in exam we need to
No,
derive.
doctor.
Ayub, continue.
I mean, in the exam, doctor, we need to derive each equation we need, right?
Yes, you need to derive the equation. Sometimes in K1, K2, K5, K6, I may ask you to derive some of these constants. Okay?
Okay, doctor. Because also in the homework, you just posted, there are a lot of equations. Those equations also, there are some basics equations. Those we should memorize them, right?
Such as?
To start, with the initial condition to find the VD, then do ID, then VQ, IQ. Those are the 13 or 16 equations in sequence to find all the initial conditions. These should be memorized, or?
You mean the initial condition calculation?
Yes.
Yes, at least you need to Yeah, you need to not to memorize. Can you derive it as we did? يعني احنا we did
Yes, we can, but for the, I mean for the exam, you know, there will be enough time to derive. We can derive.
the exam will be customized to the time. يعني don't worry about this. But at least you know you can start from scratch and do the procedure. I hope no procedures are clear, and you can proceed. يعني just you have some equations, we derive them, and then you can solve these equations together by substituting here and there and combine this, eliminate this parameter, and so on. يعني it is not يعني it is not يعني يعني difficult thing, but I think if you know the procedure, you can proceed easily. يعني.
Yes, honestly, doctor, the procedure is very clear. You know, it can be derived. So
That's what we need from you. And you know the procedure, and you know to and how to يعني reach to whatever needed. يعني. But I am not asking you if I need certain equation to be memorized or to be ready, I will put it in the like a sheet or something like this, formula sheet or something. Okay. Okay. So having this equation and the VD VQ, you can express it here, and then you can have the ID and IQ on one side, and of course you can multiply by the inverse of this. So you can end up with the this equation. ID IQ equal to, these are constants. Of course, these constants come from the inverse of this matrix multiplied by this. Okay, and you have also R1, 2, these are another constants, which is R1, X1, R2, X2. These are other constants. It's not the same here. So linearization of this equation results in delta ID, delta IQ equal to YD YQ, delta EQ prime. V infinity ده طبعا ده constant, doesn't change. These are constants, and you have here sine delta. If you replace delta by delta plus delta, and cosine also delta here, so you have sine and cosine delta plus delta. If you expand this gives you what? If you expand this, so this is sine delta, cosine delta plus cosine delta sine delta. If delta is very small, يبقى this cosine equal to 1 and sine delta equal to delta. So this will be as such, and the cosine also can expand it. Cosine delta minus sine delta delta. This delta is approximated equal to sine delta, and this cosine delta is very small, so you can have it here. Cosine equal to 1. So if you expand this with delta, you can have another two constants here, which is FD and FQ. FD, FQ combines all whatever here. So the derivation of K1 and K2, you can have X1. طبعا of course when you multiply the inverse here with this matrix and you combine, then you will end up with the FD and FQ and all these constants. You can easily derive this. It is not a big deal. X1 will be equal to this, and R1, X2, R2, Z square equal to this, and the YD constant also, YQ equal to this, and the FD will be equal to this, and the FQ is a constant equal to this. So these are constants, depends on the initial conditions. And to find the FD and FQ, you need to replace here delta by delta 0 to get the value at this operating condition. And also for the other here, for YD, YQ, these are the C1 is already derived earlier, X1, X2, all of this, these are the parameters of the system, admittance, impedance, and so on. So this is FD, FQ, and also FD, FQ equal to this combination of this. And this is we know. So you can express a delta ID from this equation. You can express a delta ID and the delta IQ in terms of EQ prime and delta delta. So these are the states. So these are states now. So we can express delta ID and delta IQ in terms of the state. And in turn, you can have delta VD and delta VQ if you replace this one by these equations. So you can get also VD and VQ in terms of the states. Delta VD and delta VQ. So we can express now the electrical power in terms of the states. So this is delta ID, delta IQ, and you have this is the power, and this substituting. Either you can derive this in this way, or and this is also okay, but also you can have it as we derived it earlier, and the delta V equal to delta VD ID plus delta ID VD plus and so on, and delta VQ IQ plus delta IQ VQ. So you replace, of course, a delta ID, real ID 0. This is VD 0. And we replace it in terms of the initial operating conditions. So these are values are known, IQ 0 and VQ 0. So all these are the values that we get from the initial condition. So this is the delta VE. So we can write delta VE equal to K1 delta delta and K2 delta EQ prime, where K1 and K2 equal to this. K1 equal to FD multiplied by this, FQ multiplied by this quantity, and the K2 equal to IQ 0 plus YD times this and YQ times this. So these are the K1 and the K2. So as you can see here, these constants depends on the initial conditions, currents and voltages and the EQ prime and so on. So this is K1 and the K2. Do you have any question? Do you have any question? Please don't hesitate to ask. Is it clear how to derive K1 and K2? The milestone is to find the delta ID and delta IQ in terms of EQ prime, delta EQ prime, and delta delta. Once you get this, you can get the delta VD and delta VQ from the algebraic equation. And once you have this, you can get the delta VE in terms of delta EQ prime and delta delta, and this is K1 and K2. Things are clear يا شباب or not? Before going to K3 and K4, if it is clear, خلاص, let us go move forward. If there is no question. Okay. K3 and K4 comes from the internal voltage equation. Field voltage, this is EQ prime. If you need to linearize this one, delta EQ prime, then you need to express the ID in terms of delta and delta EQ prime. You have a delta ID. We already derived the delta ID in terms of delta EQ prime and delta. We have that equation in the first derivation of K1 and K2. So if you have delta ID, you can express it here. And then in this case, you can express the EQ prime in terms of EQ and delta ID. You express it here in terms of this. So you can have this equation as such, and you replace delta ID by its value. So this is delta EQ, delta FD, and delta ID. We will replace delta ID by its value in terms of delta EQ prime and delta. So this is delta ID from that equation. So you can derive again delta EQ prime equal to whatever here. This becomes in terms of all the states that we have here. EQ prime, if they are the states, delta is the state. So you can express them in this. So you can combine this as K. And of course, we have here delta EQ prime. We will bring it in here in this this side, and we can define a K3 here, and we can define also K4. This is the state. So K3 equal to this, and the K4 equal to this. And all these are constants. FAD maybe depends on the initial conditions, but it is constant if we linearize around a certain operating condition. So this is K3 and K4 from the EQ prime equation. Any question? K5 and K6 comes from the terminal voltage. We have a terminal voltage equal to VD square plus VQ square. If you replace it VT by VT plus delta VT, VD plus VD, delta VD, and VQ plus delta VQ, and then you can expand this. So you will end up with this equation. So you have 2VT0 delta VT equal to, of course, when you have the linearization also, you can linearize by differentiation, and you can linearize this equation instead of having VT plus delta VT square and so on, and you expand and then you combine and you neglect the second order terms and so on. You can have this equal to a derivative of this, which is 2VT delta VD equal to derivative of this, which is 2VD delta VD plus 2VQ delta VQ. So this is also linearization of that equation. So this is what we have here. So you can eliminate it too. These are the initial values, which is known already, calculated. So you can write delta VT equal to, in terms of delta VD and delta VQ. And you will replace delta VD and delta VQ in terms of delta EQ prime and delta. So you can express now delta VT in terms of the states, delta EQ prime and delta delta. So you have it as such. You have a VD and VQ, and it's already delta VD is calculated here, XQ delta IQ, and the IQ is already there, and the delta VQ equal to this, and you express delta ID in terms of delta EQ prime and delta delta. So you can express delta VT as a constant delta delta K6 delta EQ prime, and of course you can combine what is the value of K5, which will be in terms of XD prime, YD, and so on. So this is K5 and the K6. K5 equal to 0 plus FD times this, FQ times this, and the K6 equal to VQ0 over VT0 plus YD plus YQ multiplied by this. So this is, we express now VT in terms of the states. So we can go back to the linearized system, and we can replace delta BE in terms of the states. We can replace also delta VT in terms of the states, and the delta ID in terms of the states. So we can have the linearized model here. Okay, so this is an example to find the constants and the initial conditions. You are given the generator parameters as such. You have the exciter, motor regulator, line impedance, load equal to this value. So you have load with this admittance parameters here. The initial state is defined as the electrical power is given, a reactive power is given, and the terminal voltage also is given. So you can go and substitute in these equations that we derived earlier. Okay, and then you can get all the initial conditions that you need. Find the initial condition and the linearization constants. Of course, you can substitute directly for the equation of K1 up to K6. This is VD0. Of course, you substitute in the equation that we derived earlier. So we have K1, K4, K2, K3, 4, 5, 6 as usual. So if you have any question, of course you can, as I asked you in the homework, you can, by hand calculation, you can do it. And also you need to develop MATLAB program that you give it the initial operating condition, B, Q, and V, and it will calculate all the quantities and also all the linearization constants. So, do you have any question, Shabab? Do you have any question? Okay, great. Right, now let us start. In this part, okay, we linearize the model. We have now x dot equal to AX plus BU. We need to design now the stabilizer or see how to increase the damping, how to increase the system damping. Okay, so you have any question? Omar, are you asking something?
No, Doctor. No.
Okay. So how to increase the damping now? Of course, as we mentioned earlier, we can have a power system stabilizer. But in order to design an effective power system stabilizer, you have here K مثلا 1 plus ST1 over 1 plus ST2. How to choose T1 and T2? What is the philosophy behind T1 and T2? How to design this controller in order to improve the damping? So this is what we will discuss here and see how the stabilizer can improve. Then what is the rationale behind this power system stabilizer? So we will see the damping requirement. As you can see here in the delta omega dot, you have 1 over m delta Pm minus delta Pe minus d times delta omega. So in order, assuming this is constant, this is 0. Assuming that this is 0. So how to, and this is equal to omega minus 1. So this is d times omega minus 1. How to increase the damping? How to reduce the oscillation in electrical power? How to minimize this deviation here from the steady state value? This is what we need to address here. So we will see the damping requirement, and also we'll see the supplementary excitation controller, or what we call the power system stabilizer. And we will see the input signals. You have a stabilizer, and what are the input signals here? This is the BSS, and this UBSS. This is the stabilizer output. This stabilizer output goes where? Goes to the summing point of the terminal voltage, V terminal, and V reference. So this is plus, this is minus, and this is plus. So you need here, this is the output signal of the power system stabilizer. What would be the input signal of the stabilizer? What parameter or what variable in the system that reflects the oscillations? The straightforward one, or usually the case, you have delta omega. You can measure the speed. You can measure the power, electrical power. You can measure the frequency. You can measure the reactive power. Some efforts in literature also they use reactive power. Some also papers in literature they use the current magnitude. Some used also the voltage magnitude. But the widely used input signal for the stabilizer is omega and V. omega and the power, or the speed and power. Sometimes you have only one signal, sometimes you have double input or multi-input power system stabilizer. You can have omega and also B are inputs to the stabilizer, as we will see in some of the typical real-life stabilizers that we have. The structure, we will see the structure of the stabilizer, all the blocks, and what are the functions of all these blocks. And we will see the state equation. Now we will derive the state equation x dot equal to Ax plus Bu. Of course, after linearizing delta BE and delta VT, and we have delta ID and delta IQ, delta VD, we can have the state equation ready now. And then we can see how to calculate the damping and synchronizing torque. Usually the electric power or electric torque can be written as synchronizing torque coefficient, this is in delta delta, and the damping torque coefficient of delta omega. How to calculate Ks and Kd? Kd is very important. If Kd is positive, that means the system is, there is a damping and the system will be stable. If Kd is negative or very, very small, that means your system is marginally or unstable if it is negative. Ks represents the stiffness of the system, how the synchronous machines and the system oscillate together. Of course, if Ks is negative or so, in this case, the system is out of synchronism. So we will see also how to, from the block diagram, how to find the Kd and the K and the Ks. Okay, now we derived before we mentioned we defined also synchronizing power coefficient, right? مش كده ولا ايه؟ So synchronizing power or synchronizing torque coefficient, when we have the power equal to this equal to B max cosine delta. This is similar to Ks in that equation. So with the increased loading of long transmission lines, dynamic stability after a major fault is increasingly important and become a transmission power limiting factor. As we mentioned earlier, if you still remember, time is over. For short transmission line, if this is short, thermal stability is the limit. If this is long, so the stability or the stability of the limit. So the thermal stability of the system, and we have here dynamic stability of the system, the limitation of the power transfer. Since the development of the interconnection of large electric power system, there have been spontaneous system oscillations at very low frequency, as you mentioned earlier, between 0.2 to 0.3 hertz. Once started, they would continue for a long period of time if there is no damping. In some cases, this would be comes unstable. Moreover, the low frequency oscillation presents limitations on the power transfer capability. Of course, as we mentioned here, for long transmission line becomes the limiting factor for the power transfer. And I have to stop here and continue next class, inshallah. If you have any question, then you can ask. Otherwise, we can stop here. Any question?